Welcome back. So in this module, we're going to look at an intro to simple cryptography. So in the last lecture, I kind of ended by talking about confidentiality, integrity, and availability. Now, cryptography is a technique that we can use to guarantee confidentiality and integrity. And we're going to look in more detail at advanced cryptography later, but for right now, we're just going to look at kind of a brief intro to what cryptography is and some simple cryptography that you can do by hand just to help you learn the concepts. So the word cryptography is Greek, and crypto means secret, and graphy means writing in Greek. And so cryptography is the art of secret writing. The basic goal is to send messages that no one but the expected recipient can read. But we can do more than that. So the idea that I can send a message that only the recipient can read means that I would get confidentiality. If I receive a message from someone and I can guarantee that it actually came from them and it hasn't been modified, then that's integrity. Both of those are things that we can get from cryptography. But for this lecture, we're just going to use the simple model that we're trying to send messages that only the expected recipient can read. So let's talk about some terminology, some terms I'm going to be using as we talk about cryptography. The first is the word cryptography. Cryptography is a method to send secret messages using some sort of code. Cryptanalysis is the technique for trying to break the code and read those messages. So if you and your friend are using cryptography and I intercept a message and I want to try and break it and read the original, then I need to apply cryptanalysis. So some additional terminology would be plain text. The word plain text means a message in its original form, and the term ciphertext mean a message in its coded form. Encryption is the process of transforming a plain text message into a ciphertext message. Decryption is the reverse, transforming a ciphertext message to a plain text message. And an encryption algorithm or a cipher is the method that I'm using in order to perform the encryption. Don't worry, we'll do plenty of examples of all of these things. So how do we know if a given cryptographic technique is secure? So I'm about to show you 3 or 4 different simple cryptography techniques. How do we know if they're any good? Well, the truth is, in cryptography, our measure of how secure a cryptographic algorithm is really just based on us letting lots of really smart people try to break it by performing cryptanalysis. And if they can't, then we assume it's secure. That's an interesting approach to decide if something is good. Just let a whole bunch of people try, and if they can't break it, then it must be fine. So the problem with that is that we might be wrong, and frequently we are. Every cryptographic technique that exists will eventually be deemed insecure, either due to advances in technology or advances in people's understanding of mathematics or something. So the only way that we know if something is secure is we just say, well, lots of smart people can't do anything against it right now, so it's probably okay. Keep that in mind as we talk about more advanced cryptography later, that that's really all we have as a way to guarantee security, is just the idea that lots of other really smart people can't break it. So let's talk about some simple ciphers, basic cryptography that you can perform by hand that we can use to illustrate the concepts. So originally, cryptography was performed by hand. The goal was to protect messages sent by couriers, people who would pass messages back and forth between large armies or cities or things like that. Now, we want to protect those messages from anyone who might intercept the courier, the guy who's transmitting the message back and forth. And we want to protect them from the courier himself. He himself might not be trusted. We may want to have him pass a message, but we don't want anyone, including him, to be able to read it. War was a popular time that simple ciphers were used because generals might want to send messages between various parts of their armies, and they don't want the enemy to be able to read it if they happen to intercept the person carrying the message. So the earliest documented cipher was used by Caesar. Hopefully you've at least heard of Caesar. And we call it the Caesar cipher. Each letter in the message was substituted by another letter that was 3 away. So that means that if the original message had a letter A, well then in the encrypted message it became D. If it was the letter P, then it became S, etc., etc. Let's do an example of that. So I'm going to draw up here at the top of the slide a little, I'll call it my key, where all I've done is I've written out the English alphabet A to Z, and then I've numbered it 0 to 25. There's nothing secret here. It's just there to help my math become easier. Now let's say that my secret message that I'm sending is attack at dawn. Okay, so I'm going to start at A, and I'm going to go over 3. So if I start at 0 here, then I'll go 1, 2, 3. I get to the number 3, which is what you'd expect, and that's the letter D. Perfect. Okay, that's what I expect to see. If I go to T, and I move over 3, 1, 2, 3, well, then I get W. And if I do T again, I also get W. If I do A, I'll get the same D I did before. So now I get C. If I start at C and I go over 3 letters, 1, 2, 3, I get F. Perfect. And the last one is K. So if I start at K and I go over 3 letters, I get 1, 2, 3. And I get to N. If I do that same process for the rest of the message, it looks like that. Now, that's a simple way to encrypt a message. And now if someone were to attack my courier and steal my message, instead of seeing attack at dawn, they would see because, you can't really pronounce that. It's just garbage. But if they knew my technique, they could easily reverse this. And ideally, if I send this message to one of my generals who knows my technique, then he'll look at the cipher text that I sent him, and he'll say, okay, this message was D, so I go back 3, 1, 2, 3, A, 1, 2, 3, T, T, A, C, K, and he can go through and he can decrypt my message without any trouble. Now, another type of cipher, a simple cipher, is called a shift cipher. And this is a generic version of the Caesar cipher. In the Caesar cipher, we shift the letters by 3. In the shift cipher, we shift them by n. N is just any number that we want. So in this case, in the Caesar cipher, n equals 3. But let's do another example, same thing, but I want to do n equals 10. Okay, so my message is still attack at dawn. I start with my letter A, and I go over by 10. I'm not going to draw it anymore, I'm just going to do it. So A is 0, if I add 10, I get 10, so that would be K. I start at T. If I go over 10, well, it starts at 19, and I go 1, 2, 3, 4, 5, 6. Oh, I ran out of letters. Oh, just wrap around. 7, 8, 9, 10. D. D. A, of course, corresponded to K. Then I do C. Okay, so C starts here at 2. And if I add 10 to that, I get 12, so that gets me M. K is at 10. If I add 10 to that, I get 20. It gets me U, et cetera, and I continue it. I get a message that looks like that. And the decryption for this is doing the same thing in reverse. If I find K, well, K is 10. Subtract 10, I get 0. That's A, et cetera, et cetera, et cetera. So encryption, you add the value. Decryption, you subtract the value. And you'll notice that when I had a wraparound issue, because T is 19, 19 plus 10 is 29. There aren't 29 letters. I just wrap around to the front and do it all and start from there. So that's a simple shift cipher. Okay, so what kind of cryptanalysis can I perform on a shift cipher? How do I break this? So if I intercept a message and I know that you used a shift cipher, but I don't know what your number was, what should I do? Well, the brute force approach, meaning the slowest possible approach, would be to just try all possible values for n. I could try every number that you could possibly pick. Well, how many different possible values of n are there? There's only 26. Because if I pick a number like 27, well, it'll wrap around. And using the number 27 is the equivalent of using the number 1. So it really doesn't matter. There's only 26 possible values. If I gave you a message that was encrypted with a shift cipher and I didn't tell you what my secret number was, could you try all 26 values and break my message? Yeah, no problem. So the question of, is this feasible? Yes, it's very feasible. In fact, it's easy to do by hand. I've made students in this class do it on a test before, and it's not that difficult. It's really trivial with a computer. How fast can a computer try 26 different keys for this message? Really, really, really fast. So a shift cipher is not very secure because I can break it, and I'm not even all that smart. So shift ciphers are not that secure. You can break them by hand, but they illustrate the point. As an improvement on a shift cipher, another thought is what we call a substitution cipher. So here's our next simple cipher. In a substitution cipher, I generate a random set of substitutions for each letter. And it'll look something like this. So I just picked this at random. A becomes Q, B becomes R, C becomes A, D becomes W, etc., etc., etc. Now, I've generated a random set of substitutions for each letter, and I want to make it very clear that each letter in this bottom row is used only once. So there's a one-to-one correspondence. A always encrypts to Q, and Q always decrypts to A. Q only occurs once in this list. If it occurred twice, then I wouldn't be able to either decrypt or encrypt properly. That would be bad. Let's do an example. My message is attack at dawn. Here's my random ordering of letters to produce my substitution cipher key. So how do I do this encryption? Okay, well, I'm going to say attack at dawn. So I go, okay, A becomes Q, T becomes Y, A, I already know becomes Q, C becomes A, K becomes V, and if I continue, I get a message like that. If I want to decrypt, as in if I'm the receiver of the message, I take my ciphertext here and I apply this table in reverse. So both parties in this secret communication need to know this table. So they need to be able to go from they both need to know the table because they're both going to use it to either encrypt or decrypt. So that works pretty well. So how can I break this? Well, if I cryptanalyze this, what do I need to do? For the brute force approach, I would try all possible letter combinations. Well, this could be a problem because there are 26 factorial different ways that you can organize 26 letters. Whenever I need to do a big number math, because I think 26 factorial is probably pretty big, I always go to Google, and Google will do it for me. So I type in 26 factorial, and it tells me, oh, this is 4 times 10 to the 26. Okay, I'm probably not going to do that by hand. That's an awful lot of numbers. So I'm not going to be able to try that many different keys. So I could write a computer program to do that, and it would probably work okay. Because 4 times 10 to the 26 is not too big for a computer to process through. So, but I want to point out something here. We don't have to break this by brute force. We could cryptanalyze it in a different way. So I want to point out, as we look at this, here's a ciphertext that was encrypted using a substitution cipher. There's a few things about this that we can learn. First, I noticed that Q is the most popular letter in this message. And I know because it's a substitution cipher that Q always corresponds to the same letter, whatever it is, in the plaintext. So that's the first thing. If a letter occurs frequently in the plaintext, then its ciphertext version will occur frequently in the ciphertext. Second, I noticed that this and this are the same letter and that they're in a row. Well, how many English words are there that have the second and third letters the same? Well, that reduces my search space, right? So actually, really what I'm looking at when I look at this word is I say the first letter and the fourth letter are the same, and the second and the third letter are the same, and the word is a total of 6 characters. Now, if I start thinking about analyzing this ciphertext that way, I can probably break what this word is. And once I break that, that gives me certain letters I can use to break the others. So the key observation here is that in a substitution cipher, basic language features are preserved. You can tell things like how often a letter occurs in the message, you can see when letters repeat, etc., etc. So to break a substitution cipher, we're going to use a technique called frequency analysis. Now, frequency analysis is a cryptanalysis technique, and it was actually discovered by an Arab, Al-Kindi, in Iraq. Now, not all letters, and his observation here is that not all letters in a language occur with the same frequency. So in English, for example, and he obviously was not working in English, but in English, for example, the most common letter is E. If you take large chunks of English text, E occurs more than any other letter. Vowels occur about 40% of the time in English. So A, E, I, O, U are the most common letters you're going to find. Vowels also tend to be separated by consonants. So if you have a vowel, the letters on either side of it are probably, but not always, probably not vowels. And we have other interesting features like Q tends to be followed by U in every instance, except, of course, the name Qatar. But for most English words that start with Q, it's followed by U. And there's all sorts of other things like that about English. And you can use those to help you break the cipher. And in fact, performing frequency analysis of this type on substitution ciphers is a newspaper puzzle. This is called the Crypto Quip. It's a little puzzle they put in the newspaper in the US. I used to watch other people, I didn't do it because I paid attention, but I used to watch other students in big lectures when I was in college who would sit there and solve this during lecture instead of paying attention. I hope that you're paying attention to this video and not solving a Crypto Quip, but I guess it could be considered part of the course if you were to solve these just for fun. So based on the fact that a substitution cipher has that issue of frequency analysis, an alternative type of cipher called a Vigenère cipher was developed. Now, a Vigenère cipher is what we call a polyalphabetic cipher. And polyalphabetic means that one plaintext letter could become different ciphertext letters depending on where it is in the message. So the letter A in the plaintext doesn't always become the same ciphertext letter. It depends where in the message it is. And that totally destroys frequency analysis. So in order to do a Vigenère cipher, what we do is we use a text-based key and modulo arithmetic to perform the encryption. In this case, frequency analysis is possible, but much more difficult. So let's do an example of the Vigenère cipher. So I'm going to expand my little cheat sheet up at the top because we're going to be doing a lot of modulo arithmetic. This just makes my life easier. So I have A through Z, 0 to 25, and then A through Z, 26 to 51. It's just going to help us with the math. So let's choose the key of monkey. Monkey is currently my youngest son's favorite word, so we're going to use that as our key. If our message is attack at dawn, then with the Vigenère cipher what we do is we write our key below it. And now we just add letters together. So we go, okay, A plus M is what? So A is 0, M is 12, 0 plus 12 is 12. So in that case, my ciphertext letter is M. Go on to the next one, T plus O. T is 19. O is 14. 19 plus 14 is 33. That gets me H. I can do T plus N. Okay, T is 19. N is 13. 19 plus 13 is 32. That would be G. And I can do A plus K. 0 plus 10 is 10. That would get me K. C plus E. 2 plus 4 is 6. That gets me G. K plus Y. K is 10, Y is 24, that gets me 34, that would get me I. Now I continue that process until I've got my whole message. Now decrypting this, you're doing the same process but in reverse. I write my ciphertext, I put my key below it, and then I subtract. So in this case, let's look at some very important observations. First, in my plain text, the letter T is repeated, but in my ciphertext, the letters are different. So that's good. We've gotten rid of that. Also, the letter A in the first instance becomes M, but the next instance of the letter A becomes K. The third instance of the letter A becomes M. The fourth instance of the letter A becomes K. So we don't have an obvious way to correlate one letter to one letter in the ciphertext. So we've really disrupted the frequencies with which things occur. We make it very, very difficult to apply language features to breaking this. Now, it's important here that the key be more or less secure. So all I need to do to share this with somebody else is give them my key of monkey, but if someone can guess my key, then they can decrypt my message without any trouble. And I want to point out that this is not some sort of great secure cipher. You're probably not going to break this by hand, but it is possible to break because when the keys repeat, the pattern starts over. So in this case here, for example, A becomes M because it corresponds with M in the word of monkey. Well, here A also becomes M because it also corresponds to the M in monkey. So little things like that can be used to break this cipher. It's just a lot more difficult to do. Now, the concept of a Vigenère cipher, though, leads us to the only known secure type of cryptography. Provably, mathematically, unbreakable encryption is called a one-time pad. And a one-time pad is basically a Vigenère cipher with a randomly chosen key that's the same length as the message. That's kind of a strange concept. The key needs to be shared between the parties beforehand, and the key can never be reused. That's the important part. Okay, so, and like I said before, the one-time pad is provably unbreakable without the key. So let's do an example. We'll go back to my same, math helper table. Our random key is FOWIFOZMQOAF, only because it's just random. It really does need to be random, chosen completely random. Here's my message. I write my key at the bottom of it, and it's the same length as my message. It never repeats. So it's not short and then repeating. Because it never repeats, that means that it can never that you're not going to have those repeats in frequency. So that eliminates that type of attack. So if I go through and I do my cryptography with this, I end up with a message that looks like that. Now, interestingly, because my key is random, it's impossible for an attacker to break this ciphertext, because I could come up with a random key that could make that ciphertext look like any plaintext. We'll do an example of that in class if we have time. But just for now, know that a one-time pad is perfect security, assuming that the key is totally random and never reused. In fact, the one-time pad was used for cryptography during the Cold War between the US and Russia and their spy agencies. What they would do is they would print up entire books of random key, and they would give that to their agents in the field. And their agents would use excerpts from that book when they encrypted messages. So they might say, okay, on page 47, starting at character 8, is where my key begins. And they would use up key to encrypt their message, and then they would cross it off in their book so that they never used it again. And the person they sent the message to also had a copy of that book, and so that made sure that they could encrypt and decrypt together. Now, in that case, of course, the only way to break the one-time pad is to steal the book, and that is what people were trying to do. But the one-time pad, provably unbreakable encryption. Okay, so let's stop for a moment and do a quick note about components of cryptography. So all the previous techniques I just described have two basic components. The first is an algorithm, something that you're going to do to the message in order to encrypt it. And the second is they have a key. And the key is the secret that you need in order to encrypt or decrypt properly. So in the case of a substitution cipher, the algorithm is knowing that you go through the substitution table and A always becomes C, B always becomes Q, but knowing to do that. The key is the actual table itself. So the algorithm is the process you use. The key is the secret substitution table. In the case of a shift cipher, the algorithm is knowing that you need to add a certain value to every letter. The key is what value you add. In general, when we're using cryptography algorithms, we want the key to be secret and the algorithm not to be secret. There's no reason for the algorithm to be secret, but the key always needs to be secret. And I bring this up because sometimes people think in cryptography that you're more secure if your algorithm is a secret too, and the truth is you're not. In general, what you want is an open algorithm that smart people can look at and analyze and decide if it's good or not, but a secret key that's used for individual messages. So summing up, what did we talk about today? First, cryptography is a type of mathematics that's dedicated to secret code. We trust a cryptographic algorithm if lots of smart people can't break it. And that's potentially a flawed issue or a flawed way to approach things, but it's the only way we have. We looked at three types of simple ciphers: a shift cipher, a substitution cipher, and a Vigenère cipher. Now, the one-time pad we described as kind of a modification of the Vigenère cipher, and the Caesar cipher was a specialized version of the shift cipher. So these three are kind of the basics that we looked at. And each of those ciphers has an algorithm and a key. And the algorithm is easily known, anyone can know what it is, but the key should be a secret.